Hello, my name is Amnai Naami, and in this video I will show you how traffic sign recognition can be implemented in the D1SOC board from Terazik. So first of all, we start defining a convolutional neural network model, also called CNN model, and our CNN takes images of 24 by 24 pixels as inputs and outputs 43 class scores. Each class score is associated to a different image, and the highest class score represents the most plausible one. Our model consists of 2 convolutional layers, 2 max pooling layers, and 3 full connecting layers. The goal of convolutional layers is to capture features like colors or borders, for example. Then max pooling layers are basically used for downsampling images. And concerning full connecting layers, their job is to take decisions and tell which class is associated to the input image. So concerning the input images, in this project we use the German traffic sign recognition benchmark dataset for both CNN training and inference phase. We note that most of these traffic signs are found outside the city, and it's hard to test the implementation outdoors. So once the model is built, we train it in TensorFlow. TensorFlow is an open source machine learning library. The purpose of training a CNN is to obtain coefficients needed for the next stage, the inference. So as you can see here, nope, oops, it was here. This is our CNN model. As you can see, it takes images of 24 by 24 pixels. Then at the output of the max pooling layer, we have images of 12 by 12, a resolution of 12 by 12. Then there is another convolutional layer, another pooling layer, and then 3 full connecting layers. This is the tool I'm using here is called TensorBoard. This tool is also from TensorFlow, and it allows us to see our built graph in more details. As we can see, these are the weights and the biases are the coefficients we need for the inference phase. This is the same for the full connecting layers. We still have biases and weights, and again. After training the model, we make the inference also in TensorFlow in order to test these coefficients and see if we have calculated them correctly. So for this we use the tensor analysis tool. This tool can be found on the same website as the German traffic sign recognition benchmark datasets. As you can see here, after applying the inference step to almost 12,000 images, we get an accuracy of 92.57%. As you can see, these images was recognized as this traffic sign, and these, for example, are well recognized, well classified. Here, when the image is quite dark, we don't recognize it very well, but well. So after this, we implement the inference phase in OpenCL. So for that, this is the inference phase implemented inside within the FPGA, and as you can see, it consists of the same layers, and each one of these layers is a kernel, an OpenCL kernel. Convolutional layers and pooling layers communicate through a channel, and for the rest of communications we pass through the memory because we couldn't do it otherwise. So these are the layers. Some of the coefficients were saved inside the local memory for optimization purposes, and well, for the completion report, these are the resources we got. As we can see, the convolutional layers take around 13 and 14% of flutes, also 13 and 15% of flip-flops, and a lot of RAMs. This is due to the coefficients. The local 3 kernel consists of the 3 full connecting layers, and this is why it takes like 37% of the available memory. Then, since pooling layers don't have any coefficients, they don't need too much resources. This is only an estimation. So we start with the top kernel called CNN, and then we have all those different implementations. And here we have the 3 full connecting layers, 1, 2, and 3. And now I'm going to show you the video demonstration. On the left, as you can see the image captured by a webcam, and on the right the inferred image on the output of the CNN. The D1 SOC board is connected to a webcam, and this webcam captures images. Oops. When images are dark, the CNN doesn't work very well, but anyway.